He's known literally throughout the universe for his groundbreaking discoveries in the field of string theory. He co-invented mirror symmetry, and he brought the notion of Calabi-Yau manifolds to the mainstream. Meet the one and only Brian Greene. Brian's a professor of physics and math at Columbia University and the author of numerous best-selling books. Join us on this in-person conversation held late at night at Columbia University as we uncover the hidden reality of our universe and delve into parallel universes and the deep mysteries of the fabric of reality. Let's go. Here we are today with a man that needs no introduction, fellow Brian. Oh, my mom at least claims she named me Brian, so people are confused with Brain. I don't know about you, but
yeah, I haven't heard that one directly, but
we have the two of the three Brians. Of course, I'm the least well known of them, but Brian Cox is of course the ultimate. Also, another Brian who gets a lot of attention. Maybe he'll come on someday, but so far he's ignored my messages, unlike you. And I want to express my gratitude. Last time I was in these luxurious offices here at Columbia University, I was beseeching you for an encomium on my book, Losing the Nobel Prize.
Oh, I remember that, yeah.
Which you graciously provided back in 2016, and the book came out in 2018. So I want to appreciate you and express gratitude for all that you've done for me personally and for the field of astronomy and cosmology and science communication. Thank you very much, Brian, for joining us.
Well, thank you.
One of my most requested, if not the most requested guest, and we have a ton of stuff to talk about today. I'll run out of energy and adrenal system excretions before we run out of questions, I'm sure, but we'll see how far we get. The first thing I want to do is, since I'll introduce you later, but I want to ask, what is, in your estimation, I call this the experimental minimum. I've had on Lenny Susskind before, and he's written books, The Theoretical Minimum. I want to ask you, what should a theoretical physicist, cosmologist, what should she or he know about experimental physics and why?
Well, look, none of what we develop theoretically has any real value if it doesn't make contact ultimately with experiment. And so my quick answer would be know as much experiment as you possibly can, right? Mm-hmm. Because that is the way in which you can make contact between abstract mathematics and the actual physical world. But the reality, of course, is there's a limited amount of time that any graduate student, any undergraduate, any faculty member has. And so you need to know the basics for cosmology, microwave background radiation, evidence for expansion of the universe, evidence for the accelerated expansion of the universe. You should know something about black holes. You should know the observational evidence from motions of stars in the Milky Way galaxy to the Event Horizon Telescope's actual images of black holes. If you don't know about that stuff, people will look at you kind of weird. And, I think it's also really good to know the basics of particle physics, right? I mean, you should know the standard model of particle physics. You should understand the experiments that give rise to the gauge symmetry of the standard model. And you should understand that in 2012, we confirmed the Higgs particle. You should know that supersymmetry has not yet been confirmed. That's an important experimental null result. And beyond that, you should understand that there is this mismatch between our calculations of dark energy, which really comes from understanding the quantum physics of elementary particles and the observational evidence for dark energy. That I would call perhaps the minimum. No doubt there are other things that should be included, but that's a good start.
Yeah, and in this building have been renowned, and this campus have been renowned purveyors of both theory and experiment. I'm thinking about Robbie and of course C.S. Wu and of course all the many great experimentalists and theoreticians who have come through this building. And I see it as sort of, and I believe Arno Penzias was a student here, wasn't he?
I didn't know that.
I think he was, but I'm not sure.
Yeah.
Well, we'll have to fact check.
But a student, that could well be, because that would have been a long time ago.
Many of them came through here. Yeah. And I think about kind of, what do I want my graduate students to know as experimentalists?
Yeah.
For me, I say you shouldn't have to do theory, but you should know theory as well as an incoming graduate student. Otherwise, and no offense to plumbers out there, Lenny Susskind, as you know, was a plumber, but you're kind of just doing plumbing and microwave electronics, and that's very important and interesting stuff. but you're a technician and you can get paid a lot more in, free industry. Actually, I was talking to Jim Simons recently, who's the benefactor, of course, of the Simons Observatory, and I believe he supports the World Science Festival.
Sure,
Yep.
yeah.
He and Marilyn are huge champions of all the great work you and Tracy do. But he was saying, once he had to call a plumber in the middle of the night, and the plumber came over and fixed up the thing and the sink and stuff. And by this time, Jim was in his hedge fund career, and the plumber said, "That'll be $700, please." And Jim is like, "Wow, I'm one of the richest guys in the world, but this is ridiculous. $700, I'm a hedge fund manager. You make $700 for 15 minutes." And I said, "Oh, you're a hedge fund manager." "Yeah, that's about what I used to make when I was a hedge fund manager."
Right.
But when you think about, technicians and so forth, you should understand the why, I believe, of what you're doing. And so I want them to understand the theory, but not necessarily to do it. And it's always kind of been curious to me, because when we let a theorist on those occasions come into my lab, we had Katie Fries over just about a week or two ago, and we don't let them into the lab because they're always, they're going to touch something, fiddle with something. But in reality, I think there is sort of a mismatch between what theoreticians do. And I wonder if you could get into that. What do you do as a theorist? It's not like saying, thing for your supper, but what does a theorist spend his or her day doing? And I realize, every theorist is different, and I'll get a different answer when I talk to Jana. But tell me, Brian, what do you do as your craft as a scientist?
Well, it's an interesting way of framing it. What do you do day to day? Because the day to day changes drastically regarding depending on what project you happen to be involved in. But I would say the general rhythm is you read papers that others have written in order to get a feel for the state of the art in whatever problem you're interested in. And more often than not, when you read somebody else's paper and you see things from a different perspective, it inspires all sorts of new ideas that you, the individual theorist, can begin to pursue. And what does that mean? You begin to say, hey, they did this calculation. What if we were to change this, that, or the other and redo the calculation? What would that yield? Or, hey, they did this calculation in this context, but wait a second, I remember this other problem from a couple of years ago. And I think that if I take that calculational method and adapt it to that other problem, there may be something interesting to do. And so it's a variety of incremental steps that are often seeded by the community. It's usually not the Albert Einstein off at the patent office coming up with this radically new idea.
Really? I get emails all the time.
We do, yes. And Einstein did a lot of great things for science, but working in the patent office, at least from the perspective of modern day physicists, was a real disservice. And I mean that in the following way that you already understand, which is so many people think you don't need to be within the community. You can be off in left field, just having big thoughts, and you'll change the world. On occasion, that happens. It certainly happened once and, a handful of other times. But for most of us, we're embedded in a community. And there's an ongoing conversation. Sometimes it's a real conversation. Sometimes it's reading other people's papers. And so day to day, that's what we do. We are pursuing mathematical developments and trying to see what insight we can extract from them.
Hey, friends, I'll keep this pretty short, but I've been doing some data analytics on previous episodes that are related to the topic of string theory, including one with my friend and Brian's friend, Kamran Vafa. And when he was on last time, you can see at the bottom there, it says the watch time from subscribers versus unsubscribers means that more than half of you aren't subscribed to the channel, and yet you're enjoying the videos. And that's just not right. No, I'm just kidding. I would really love it, though, if you would consider subscribing, because it really helps me get some of the guests that we're getting on. And we're poised to get some phenomenal guests. But when their agents or their publishers look at podcasts, they have to say, well, is this worth me sending my beloved author or thinker to appear on? And a lot of times they do that, unfortunately, just based on sheer number of subscribers. So I wonder if you could do me a favor. It would really help a lot if you would subscribe. And I promise in doing so, you'll help me help you bring the best guests to this podcast that we can possibly get, and onward into 2024 and beyond. So I really appreciate your help in helping us grow the podcast. Now back to the conversation with Brian Greene. So you're no doubt familiar with the fact that string theory has come under attack, and you've been actually gracious and kind enough to participate in debates with past guests on the podcast like Eric Weinstein and of course, Peter White and many others that have alternative theories, alternatives to string theory. And you did your thesis, I believe, in 1986 on string theory, which is, kind of the salad days. And I want to ask you, if you had to prize string theory, I asked Mike Turner about inflation and dark energy recently, gave him the same thing. Give string theory a grade, a report card, and break it down into the subcategories of string theory. Where is it succeeded? Where does it need more work? And where is the parent-teacher conference going to happen?
The only reason I'm laughing is because the 25th, and this is not a plug, folks, so it doesn't matter, but it's just because you asked the question. Yeah. The 25th anniversary edition of The Elegant Universe is coming out in August. And on the final pages of this new chapter I've written, I give string theory a report card. So part of me is like, hey, I don't really want to spill the beans here, but I'll give you a rough feel for it. Yeah. So it's a good way of phrasing it, because you need to judge a theory among many different criteria, right? And some string theory is done extremely well, and some it hasn't done as well. So let me start with the stuff where it hasn't done as well. Mm-hmm. When it comes to making contact with experimental data, the very question that we began with, string theory is not as far along as I would have hoped, right? So back in 1986, I don't want to calculate how many years ago that was, but it was a long time ago. And if you would have asked me then, and I think most string theorists at the time, 2023, are we going to know through experiment or observation whether these ideas are correct? 95% of the community would have said, of course we'll know by then. And yet here we are, and we don't know. So on that, I would give a relatively low grade, but I'm going to come back to how I'll give the final grade on that in just a second, because the theoretical developments in string theory have been so astonishingly powerful, well beyond anything that I would have anticipated back in 1986. And one development in particular that no doubt you know something about, because it's the most famous development in the last 20 years, this ADS-CFT correspondence by Juan Maldacena. And actually, it's a whole community of people, of course, but Juan wrote the paper that really took the world by storm. The relevance of that, well, it's got a huge degree of relevance, but the relevance to the experimental question is interesting, because once we learned, as we did with Juan's insight, that string theory is not as a radical separation from previous methodology as we once thought, which is a great development. There's a deep connection to older techniques that are still at the forefront, because they're our most powerful techniques, quantum field theory. Once you learn that quantum field theory and string theory are joined at the hip, which is what Juan showed us, quantum field theory is the most powerfully tested theory in the history of particle physics, in the history of quantum mechanics. It's a framework that works.
Tested in what sense? Tested in terms of internal consistency, philosophical expediency? In what way has it been tested?
I'm talking flat-footed here. Mm-hmm. Take the standard model of particle physics. It's a particular quantum field theory, and that particular quantum field theory makes predictions that we can confirm. I mean, take the magnetic moment of the electron, right?
Decimal place.
Yeah, is that not the most insane thing? I think
it's the most accurately known number.
Yeah, so think about the fact that you can do a calculation using this framework of quantum field theory. It agrees to observation to that many decimal places, right? So that's the sense in which these ideas have been rigorously tested. When you learn that framework is intimately connected to the framework of string theory, that they're not these two radically different things, which is what we initially thought, it doesn't prove string theory, of course, but it shows you that we are within the same universe of ideas all of a sudden. And that, to me, mitigates to some extent that string theory has not gone as far as we had hoped to actually make an experimental prediction that we can confirm. But the fact that it has joined together with the most experimentally tested approach, that is good. That's strong.
So one of my favorite canards is that I feel like you, and I'm going to say this, some of my best friends are theorists. I don't know if I'd let my daughter marry a theorist, but anyway, the point of string theory and all of experimental or all of science within this context scientific method is to make some connection with reality, and as you call it, the fabric of reality, so beautifully and poetically. But I feel like some of your ilk have and including when I talked to Shelley Glashow on the podcast a couple of years ago, I said this to him as well. I feel like many of your colleagues, not you necessarily, have put what I call the toe before the gut. In other words, we are searching for a theory of everything, and string theory is a candidate theory of everything. I believe that's safe to say. And yet, necessarily have a grand unified theory that people agree with. I mean, Shelley had his SU5, and there are many different instantiations of it. But to my knowledge, and I'm just a humble experimentalist, but tell me, why do we skip? Why aren't there as many people pursuing in the sociology of science pursuing guts, grand unified theories, which would maybe can explain the difference between a theory of everything and a gut? But why are so many people over-indexing on toes versus guts?
So first of all, I don't use that language much. I mean, sort of grand unification, certainly, but TOE, theory of everything, is a term that I tend not to use very much, really for sociological reasons, that if you're working on the theory of everything, then what is somebody who's not working on it doing with their time? Theory of nothing, so I've never really warmed to that idea. But of course, that's not the point of your question. The question is, where should we be putting our energy? And the way I would say it is this: if Shelley's SU5, or if the other grand unified theories like SO10, for the people who are not in the know, these are just names of certain symmetry principles that equations can satisfy. And we've learned that symmetry is vital to formulating the laws of physics. And as we went further along in physics, we invoked ever more robust symmetries, and those are two examples of them. Had those theories borne fruit? That is, had their predictions been directly confirmed, which could have happened, right? Because Georgi, Glashow, and their approach, it predicted, their grand unification theory predicted that the proton should decay. And as we all know, we searched for that decay, no sign yet.
Still waiting.
So that was certainly, I think, sociologically why people didn't just put all their energy into going in that particular direction. But I think that the deeper answer is that we've come to realize that to go further in physics, you've got to understand how gravity and quantum mechanics coexist. And all of the work on grand unification ignored the force of gravity. That was not the way that people were pursuing the next step in our understanding of physics. And so to leave out gravity is to leave out an essential part of the story. And when string theory came along and provided a means for putting gravity and quantum mechanics together, that was deeply alluring to so many people, because now all of a sudden you weren't leaving anything out. Right. So it could be the biggest unification of all. And moreover, when we began to study string theory, we began to see the more conventional grand unified theories like Georgi and Glashow's SU5 and like SO10. We began to see those emerging from the unification of gravity and quantum mechanics. And so it felt as though we can have our cake and eat it too, right? We can put gravity into the story and we can unify everything.
Well, let me just push back with love and respect, as my hope is my trademark. But say, imagine a counterfactual history where Shelley and Weinberg and Abdus are working, and they say, well, we're not going to look at electroweak unification until we can incorporate gravity and the strong force into it. Wouldn't we have been stymied and flummoxed for an additional, who knows how? We could still be looking for electroweak unification.
Two quick answers to that. One is absolutely, right? So I would never advocate that every single theorist goes along and tries to get the big prize of putting gravity and quantum mechanics together. So certainly I would say that you do need people who are more phenomenologically oriented, trying to come up with theories that are closer to data. And that's, of course, what Glashow, Salam, and Weinberg were doing. That was a time when the particle physics data was right there. It was right ready to talk about how do you put electromagnetism and the weak nuclear force together. Because after all, it was 1979, I think, is when they get their Nobel Prize. But the paper itself was in the early 70s. Well, late 60s is Glashow, and then early 70s. So it was only 7 years away or something, 8 years away. So the theory and the experiment were pretty close, temporally speaking. So that's wonderful. You need people who are having this ongoing dialogue with phenomenology, and that is what was happening. Today, we are, as people often say, the victims of our own success. The open questions are at length scales that are so tiny, energy scales that are so huge that we simply don't have an accelerator that within 7 years is going to probe the scales where the open questions currently lie. And that's why we've gone so far beyond what experimenters can do. And that's why here we are 40 years later with string theory, and I don't have any experiment to show for it.
Well, I wonder how you react to a statement made by our mutual friend Kamran Vafa when he was on the podcast a couple of years ago. I said the same thing, which is a canard that we experimentalists use to tease you brilliant theorists. We say, string theory hasn't made any testable predictions or connections to it. He said, Brian, you're wrong. And he's such a gentleman, as you know. He said, Brian, you're wrong. String theory predicts the mass of the electron. I said, holy cow, tell me more. And he goes, within string theory, it's possible to come out with a calculation that shows the mass of the electron should be between something like 10 to the minus 1 Planck masses to 10 to the minus 30 Planck masses. Okay, so it's 30 orders. And he said, I know that's not good. And it's like me saying to you, you weigh less than 10 to the 26 kilograms, which I think is accurate, but not precise.
Yeah.
And so when you hear things like that, as an experimentalist, I feel like it's hopeless. And I would only think that, well, to what extent should we continue to index on a young Brian Greene, going into or Keating, going into this field where sociologically we can ignore, but just in terms of intellectual satisfaction of having something complete and visceral that you could accomplish in 6 to 7 years.
Yeah, I think that's all good questions. And let me just jump off from what Kamran said.
Yeah.
I mean, Kamran's, a dear friend and one of the most brilliant people. So, and I know exactly where he was coming from on that particular answer, but I can well imagine how it doesn't feel as satisfying as you had hoped when he initially said
That's
it.
right.
So let me give another unsatisfying answer that one can give too. I'm sure you've of course heard it before. String theory does make a prediction. It predicts the existence of gravity. Now, before anybody rolls their eyes, there's something really, really deep here, which is the following. You, a moment ago, said, imagine an alternative counterfactual history where Salam and Weinberg and Glashow hadn't done their work, what would have happened? Imagine another counterfactual, another possible universe where there wasn't an Albert Einstein who came up with the general theory of relativity, okay? But imagine instead that we found string theory. By working on string theory, which does not have gravity manifestly in its equations from the get-go, string theory truly is a theory that describes the motion of vibrating filaments. There's no gravity in there per se, right? But if you study string theory, the mathematics of it, you find that there's a vibrational pattern of a string, which has exactly the right properties to be the quantum mechanical conveyor of the gravitational force, which means when you study the motion and properties of this particular vibrating string, you study it close enough and you find Einstein's equations. You find Einstein's equations. Einstein had to spend 10 years from first principles banging his head against a blackboard to try to learn differential geometry and to come up with the Riemann equation, and all of this deep differential geometry, and he comes up with the Einstein equations. Had he not done that, we wouldn't have had it. But had string theory come along and people studied it, they would have extracted what we now call the Einstein equations from the theory. So that's pretty darn deep right there. I was
going to say, is that in a similar vein that you could derive Newton's equations or even classical mechanics from quantum mechanics? Or is it completely different?
It depends. So if you're talking about how you can get sort of something akin to F equals ma from Schrodinger's equation.
Einstein's Newton's theory of universal gravitation.
Yeah. So I don't know how to get that from quantum mechanics. I do know how to get F equals ma from quantum mechanics.
F equals, I'm sorry.
Yeah.
I was maybe conflating two different things. I was asking, the first time analogy I asked was, can you get it in the same way that you're saying you can derive Einstein's GR from string theory? Can you also, is it in the same vein technically, mathematically, as the way that we can derive Newton's law of gravitation from GR? In other words, would you predict this? Can you also say, does it predict it in the same sense that GR predicts Newton?
So in a sense, yes, right? But the difference is in the string theory context, you are unifying Einstein with quantum mechanics,
Yeah,
something
which is
Einstein
weird.
had never
Right.
done.
Because I should say, it's a classical
Yeah.
theory emerging from a quantum
Yeah,
theory.
and then you're pulling out from
Einstein.
that the classical gravitational equations that
Excellent.
Einstein wrote down. And so many of us find that to be, is it really a prediction in the conventional sense of go out and look for this? No, it's a post-diction. We certainly knew about gravity and Einstein's equations beforehand. But, let me ask you this question. Had we had no Einstein, and had we had string theory, and some string theorists pulled out of string theory Einstein's equation and made a prediction for the bending of starlight, and then we went out and measured during a solar eclipse the bending of starlight, and it was confirmed, wouldn't you feel, oh my God, string theory
is the
it's all right? Wouldn't that be where you go? So in this other history,
the counterfactual, the Greene counterfactual history, I would be forced to at least grapple with it. I think the ultimate base level of the fabric of reality, to use your poetic language, it would be a less satisfying, less nourishing intellectually than, say, discovering these extra dimensions in, say, a particle. Because you could also maybe extrapolate the other way. Could you get quantum field theory from string theory? If it counterfactually, Schwinger wasn't in this building and didn't come up with Feynman and Tamanga, and he didn't come up with QED, could you get that emerging from string? I assume the answer
and
is yes.
And the answer is yes.
Yeah.
Hey everyone, we're talking about space and time in this episode with my good friend Brian. Thanksgiving season is upon us, and as you can tell, I'm very thankful my kid's favorite Brian appeared on Into the Impossible. For many, Thanksgiving means good old American traditions like family turkey dinners, football, arguing with your loved ones, and of course, Black Friday discounts, my favorite day on the calendar. And if you spend a lot of time on your computer like I do, you need to check out the Black Friday deals that AppSumo has on software tools. All the deals are available right now until December 1st. This deal covers all sorts of software, courses, and more. And the discounts are huge. As big as the universe. I'm looking at their website right now, appsumo.com, and I'm seeing 80%, 90%, 95% off. Are you kidding me? Wow, this is truly an impossibly good deal. And for me, this Black Friday, I'll treat myself to a tasty treat, Tidycal, which helps me manage my calendar easily and efficiently, and it will do so for you too. How do you think I stay in touch with all my guests back and forth? It's just like Calendly, without the price tag. As you can expect, balancing my professorial duties with podcasting gets a little bit tricky. And this product is going to help me stay focused and organized so I get everything done on time. Personally, I've used Calendly a lot in the past, but it's pretty basic, and in my opinion, it's overpriced. Tidycal has the same cool integrations and almost infinite customizability. It's remarkably easy to use. Plus, it's a lifetime deal. So no more monthly payments, regardless of whether you use it or not. For a one-time super low price, you can get lifetime access. So you can finally master the fabric of reality, at least regarding your personal time anyway. And Tidycal isn't even a part of the Black Friday lineup, which means that there are 30 plus other tools available with even bigger discounts for a limited time only. I love apps like this for cutting through the clutter and back and forth scheduling interviews, collaborators, friends, and guests, and even those occasional rock stars like today's guest, Brian Greene. So once again, for all of you listening and watching out there, check out AppSumo's Black Friday offers at appsumo.com. The sale is running till the end of November, so go to appsumo.com and make sure you take advantage of these amazing deals. Now, back to the episode.
Then you'd have to ask, well, what are the classical emanations from which that we could test with particle accelerators or cosmological accelerators, which I want to get into, the universe as a laboratory. So yeah, that is certainly, I think you ask, well, what is the difference between counterfactual and or let me say this, a retrodiction or a postdiction and a prediction? I kind of don't believe that the job of a scientist is just to make new predictions, because there's an infinite number of things that could be possible, and there's a very, very small set of things that are possible and are testable. So Einstein's perihelion of Mercury, anomalous precession of the abscess of perihelion, that is a retrodiction, but it was very powerful. And then from that, yes, there were new things that came along. I think it would be, the coolest thing, and I'm going to ask you, for other speculations when it comes to things like string theory or the multiverse, which are both domains that you've trafficked in very successfully. But when we think about what is it that the goal should be? Can it be to make a connection, to make something that my experimentalists, my colleagues can test in a laboratory or not? That's technologically dependent. That's situationally dependent. We wouldn't have been able to discover, and I love to read like the original. You were talking about Einstein in the patent office. If you read like Maxwell's original treatise on electromagnetism,
hard to read.
It's hard to read, and the fluxions and everything. And he was like inventing new terminology. But ultimately, he got the right answer because he came up with these 4 equations that are tattooed on many people's foreheads in this space. But if you look at the underlying physics, the model for it, it's a bunch of claptrap, weirdo, occult stuff with wheels and gears and electromagnetic virtue. I always joke, like, what if he was on Twitter? What if Twitter exists in 1865? And he's like, I got this great theory, and it involves these whirlpools and eddies. But like, people have said, you're an idiot. Like, there's no whirlpools and eddies. We already know that. But then to look back, you would have thrown the baby out with the bathwater of the electromagnetic virtue because you could have rejected a correct theory. And I worry that we're doing that with string theory, or I'm worried that in some sense, the nutrients in the earth, there's only so much nutrition. So are we neglecting other models? And I guess I want to ask you, I've asked this of other people, Stephen Wolfram, Eric Weinstein, Garrett Lisi. Whenever I ask them, what do you think, not about string theory, because I know I'm going to get an earful about string theory from all these gentlemen, but what do you think about competitor B? What does Eric Weinstein think about Garrett Lisi? Or what does Garrett Lisi think about Peter Woid or Stephen Wolfram? And they'll say, I don't have time. And I'm like, come on, guys. I've got little kids. I've got teaching responsibility. I've got an experiment in Chile. I'm not nearly capable to comprehend the mathematics. But at some level, you don't have time. I mean, string theory, your thesis, I'm not going to date you, but it's over 30 years ago, right?
Yeah.
Do people really not have time in the theoretical community to actually preview? Or is it like, you only have so much time, so I'm not going to devote unless I can do it to everything?
Well, I guess what I would say is, when any of these newer ideas have come online, there's usually been some string theorist who has spent some time on it. And if it's someone who I respect, then, my motivation to then redo the analysis and try to confirm what my colleague has concluded, I feel less motivated to do it. So I'll give you an example. I believe it was with Garrett Lisi's thing that Jacques Dissler, do you know him from University of Texas,
I know
Austin?
his name, but I don't know.
Yeah, so Jacques is a brilliant theorist. He and I we used to work very closely together a long time ago, back in the 80s. We're still, good friends. Every time I go down there, we hang out. And he wrote a variety of things on Garrett's ideas. And I perused those. And I trust Jacques. He's one of those people. I mean, it's not like you go and redo every experiment. Everybody does, So I trust him. He's a thoughtful person. And the conclusion that he reached was, there's nothing here. And when I read something like that, I'm like, okay, I don't feel the motivation. When it comes to Stephen Wolfram, I do feel differently. I do want to put some effort into understanding exactly what he is saying. Again, I know him reasonably well. We're not best buds, but we're friends. And he's encouraged me a few times and he sends me articles, and I am starting, for instance, to do that now. He and I are going to do a conversation at some point in the not too distant future. So I will be educating myself on that one. In terms of the others, loop quantum gravity, I did maybe 15, 20 years ago. I put a little bit of time in so I would understand the basic framework that they were developing. And I found it interesting. It's not in any way crackpot, but I didn't find it sufficiently compelling. And I also didn't like the fact that, unlike string theory, it didn't naturally incorporate everything, all forces, again, staying away from theory of everything. There is an appeal, nevertheless, in string theory that it's got the capacity to embrace everything. So on those, that's sort of where I stand. Did I leave somebody out of the discussion?
Eric Weinstein,
Eric,
your friend, you guys have debated, and you had a memorable exchange at the IAI conference where he said something and you said, well, maybe we were over exuberant. And he said, like the My Lai massacre, as only Eric Weinstein could do. So his geometric unity theory, which features some testable predictions. And again, I'm an experimentalist, right? So I'm looking for, well, what things could we do? Say, how would the prediction of Garrett's theory or Stephen's theory or Ava Silverstein, any idea, how will that affect observables that, say, the Simons Observatory can measure? One of the things we can do is measure abundances. We can look for spin-dependent phenomena and those theories. And I think the thing that Eric always harps on is that we don't we seem, not to say we collectively as physicists, and I'm including myself, even though I'm not a theorist, but in the things that seem to not trouble us, troubles Eric. In other words, why is it that we have three families of fermions, and we don't have an explanation for it? We just sort of know it as a taxonomy. And as Feynman said, just because you know the name of something tells you bupkis about it, right? Does that trouble you? I mean, is that part of?
Hey, if you go back,
yeah,
you mentioned my thesis,
yeah,
which I haven't thought about in a very long time. But the point of that thesis was to try to answer why there are three generations from a string theoretic perspective. And way back then, there were only a handful of known shapes for the extra dimensions that string theory requires. And in string theory, the number of generations of particles is related to a geometrical quantity in the extra dimensions, half the Euler characteristic for those who are keeping score at home. And so if you have three generations, you're looking for Euler characteristic 6.
Okay.
And there were only really 3 known examples that had been constructed around those times. And with a colleague, another graduate student at Oxford, we proved that 2 of them were actually the same.
So unified.
So we unified them. So we're sort of down, by 1. And I may be aggrandizing, but I think we also pulled in the 3rd one. So I think we basically got it down to 1. If I'm maybe being generous with myself 40 years later, but it was 1 or 2. I believe it was 1. And so what we did was we then went further and tried to calculate the mass of the electron or the mass of the other particles from this particular geometrical form for the extra dimensions. And at that time, with the limited mathematical understanding, which has since become much more deep, we got partway down that road. But as we did, more and more shapes for the extra dimensions were discovered. So all of a sudden, this motivation to study one, well, if there are only 4 or 5 total and only one with 3 generations, of course you're going to study it. But then when there are 500 or 10,000 or 10 to the 500, your motivation for studying any specific example drops precipitously. So that is the historical way. But yes, does it intrigue me, this question of why there are 3 generations? Absolutely.
When I interviewed Nick Bostrom, who Nick
sure.
Bostrom is, so I said to him, he's from Sweden. I said, look, Nick, you're from Sweden. And if I had on, ABBA, if I had them on the Into the Impossible podcast, and I did not ask them to play Dancing Queen, it would be a complete dereliction of the podcaster's oath, which you and I have sworn to. I have to ask you, Calabi-Yau manifolds, because I'm here with at least, the foremost, proprietor of all things Calabi-Yau. What is a Calabi-Yau? What is a manifold? How does it have to do with the fabric of reality?
Sure.
Could you join us with this no doubt delightful explanation from the godfather of the Calabi-Yau?
Yeah, I mean, very briefly. So I think as many people know, when we studied the equations of string theory, even as far back as the 1970s, it became very clear that the theory required more than the 3 spatial dimensions that we all see in the world around us. Indeed, we needed 6 additional spatial dimensions that we don't see. How do we explain them? This goes way back to Kaluza and Klein in the early part of the 20th century. Just imagine that the extra dimensions are here, but they're crumpled to a size that's so small that we can't detect it with the naked eye, and perhaps even with our most powerful magnifying equipment, even with accelerators, perhaps it's just too small. Good. So that's why the dimensions would be tiny. But then you say to yourself, can you curl them up in any which way? Or are there mathematical restrictions on the geometrical shape of the extra dimensions? And indeed, there are these restrictions. And the particular kind of restriction that people began to study in the 1980s was to demand that the theory preserve this thing called supersymmetry, which we made reference to very briefly before, not finding it at the Large Hadron Collider. But in any event, the goal was to preserve this symmetric quality of the equations. And when you impose that, you find that the extra dimensions have to be curled up into this so-called Calabi-Yau shape or Calabi-Yau manifold. A manifold is really just a geometrical shape. There's some technical details, but that's the basic idea. And so what is a Calabi-Yau shape or manifold? Well, it's a manifold that preserves, or perhaps I should say it in the following way. It's a manifold that is as close as you can be to being flat without literally being a flat shape. So you might say, well, what does that mean? But in 6 dimensions, you can have something which is known as Ricci flat. It's a kind of flatness that was developed in the early days of differential geometry. And so you can have the shape that's as close as it can be to being flat and yet not literally being flat itself. For those who want to know a little bit more detail, the idea is if you take a vector on this space and you parallel transport it around any loop, it comes back to itself up to a symmetry transformation. And that symmetry transformation is demanded to line a particular group. And what is that group? That group is SU3. So that's the idea of this particular kind of shape which solves the equations of string theory and preserves supersymmetry at low energy.
Do those have Euler characteristic 6, or do they?
They can have a whole variety of Euler characteristics. And so as we've studied these more and more, the range of numbers has grown, but roughly speaking, call the Euler characteristics a number between, that's less than, say, 1,000. It can be negative, it can be positive. So there are a lot of possibilities in there. Euler characteristic 6 would be the preferred number if you're trying to make contact with particle physics as we know it. And over the years, more and more of the Euler characteristic possibilities have been developed.
Do we know there will be no other forces, discovered? I mean, we hear about these fifth forces.
Yeah.
Those are sort of esoteric in the force space. I call, if the muon has this anomalous moment, then it might be mediated by these virtual particles, which themselves would be a byproduct of bosons, which are the gauge, force mediators. Honest to goodness forces. I mean, do you believe there are possibilities that there could be something as manifest as gravity or Yang mills or whatever that we would identify that's an honest to goodness force? Or can we not say right now that we will never or we will ever discover a new force, a new proper force?
So there's sort of two answers to that question. One is in string theory proper, there are many versions of the theory that do give rise to other forces. For the most part, these forces aren't manifest at the energy scales that we have access to. So they would only come to life, if you will, if you're probing the universe on incredibly short distance scales or incredibly high energies. But the other answer is, look, if you have additional forces that most of the particles that we know about are immune to, then those forces won't have a whole lot to act upon that we have observational insight into. So can you have additional forces that persist even at low energies? In principle, yes. Now, there are bounds that come to this, mostly from cosmological perspective, because there's a limit to the number of degrees of freedom that you can have commensurate with the expansion rate of space and things of that sort. So is it possible that there are extra forces? Absolutely. Is there any evidence for it? No. But string theory has an abundance of additional forces at higher energies.
So back in the days of yore in 1986, there were two movies that changed my life tremendously. One was Top Gun, and the other one was Back to the Future. And a recent paper of yours, co-written with our good friend Jana Levin, is shown here. I read through it. Back to the Future, Causality on a Moving Brain World. I want to get into this. I want to say, first, again, thank you for that explanation of Calabi-Yau, and thank you for the connection between three generations of fermions. I want to get from you, what is brain world? But before I go there, what interests me most lately, most cosmologists sort of assume inflation or something like inflation occurred. And I often like this term, which actually David Albert, your colleague and our mutual friend, told me, actually, this saying originally came from philosophy of science. But you'll know it from Natty Seiberg, who said, if anything comes up, that looks like string theory, that's not part of string theory, we'll just call it string theory. He said something along those lines.
Right.
David said that anything that I think a philosopher of science that David's like screaming at the camera now, telling, because he just told me 20 minutes ago or so. But he said that a philosopher of science said, when we discover something in the philosophy of science, and then later it gets incorporated into physics, we just call that physics and say the philosophers didn't help us at all. We'll talk about philosophy, hopefully, if you have the energy, as I'm getting my second win now late at night here in upper New York peninsula of Manhattan Island, rather. But I want to first ask you, when I look at exciting things to me, it may be that inflation occurred or something like inflation occurred. We'll get into alternatives to inflation in just a bit. But those alternatives might look a lot like inflation. The alternatives to string theory might be subsumed within. But one thing that seems so different from all the, it's like the platypus of mammals or whatever, is Lorentz invariance. And if we were to show there was a violation of Lorentz invariance, I think it would be almost a bigger advance or a bigger crisis in science than, say, proving that inflation took place or motivating that inflation took place through CMB studies that are I'm involved with. What are your thoughts about a Lorentz invariance? Is it sacrosanct? And maybe you could give a quick definition. Some of the work was done by Madame Wu in this building with parity violation, which is a kind of an offshoot of Lorentz invariance. What is Lorentz invariance? Why is it central to string theory? How does it play a role in this theory and moving in Back to the Future?
So Lorentz invariance is much bigger than string theory. It predates it, and it is a fundamental symmetry property of just about any theory that we take seriously. And the idea really goes back to Einstein and, of course, Lorentz, who in the early years of the 20th century, even actually the later years of the 19th century, were thinking about Maxwell's equations that you made reference to, and noting that within those equations, there's this deep symmetry principle, which in modern language basically says that any perspective that's moving at a fixed speed in a fixed direction, constant velocity motion, is really as good as any other perspective moving with a different speed in a different direction. So it's describing an equivalence or really lack of preferential frame of reference when you consider the constant velocity observers that might be examining the world. And we do, at least in a local environment, consider this to be a sacrosanct symmetry. This is what gives rise to the special theory of relativity. This is what gives rise to the speed of light being constant. The way the symmetry is realized, light has the special quality of its speed being fixed. And so the data behind this and the experimental confirmation of this is so strong over the past 100 years that people would be loath to give up this idea. But the one thing I want to stress relevant to our paper is the symmetry really is confirmed in a local sense. I mean, those are the experiments that we do. We consider some region of space over some interval of time. And within that region, call it the laboratory, call it your home, call it whatever. We do our experiments and we establish this to be true. What we considered in our paper is not whether Lorentz symmetry, Lorentz invariance would be violated in any local environment, but we wondered, what if the overall grand structure of space-time is such that the symmetry is violated not locally, but only in the global sense? What do I mean by that? Well, imagine that space doesn't go on forever in a given direction. Imagine that if you go out in one direction, you go far enough, you wind up returning to your starting point, much as what would happen on the surface of the Earth, of course. And so we imagine that idea applying to the fabric of space. And in that environment, there are subtle violations of the Lorentz symmetry. You would never detect them locally. Rather, you'd have to circumnavigate the universe in some sense.
The laboratory or the bulk, or is it a micro dimension that you're circumnavigating?
I don't care what size the dimension is right now. So I'll be agnostic on the size of this extra dimension. And the interesting thing is to ask yourself, if you redo Einstein's analysis in a universe that has this non-trivial shape for one of the dimensions, how does it change what Einstein did way back in 1905 with his special theory of relativity? And we found some surprising results. We found that you can send signals in this universe at a speed that's actually greater than light speed.
Is it always greater, or can it be greater? It can slow down, it can have refractive properties.
So if we get a little bit more into the detail, you mentioned this idea of a brain before. So that's one of the key ideas here. We imagine that our universe is living on what I like to poetically think of as a giant slice of bread that itself is floating in a larger environment. So imagine everything that you know, just for visualization purposes, takes place on this giant slice of bread universe. Obviously, it's only 2 dimensions of space, but in the real version, it would be 3, but it's too hard to picture. So let's do this lower dimensional version. And imagine, that's right. So this slice of bread is called a membrane or a brain.
Yeah.
That's where this idea of brain comes from. And it's a very natural idea in string theory to envision that the universe, as we know it, takes place on a 3-dimensional membrane, but the 2-dimensional version of the piece of bread is a good one to have in mind, because then you can picture it. But imagine that perpendicular to that slice of bread is an additional dimension of space, and that our slice of bread can move in that additional dimension of space. And imagine that that additional dimension of space has a circular shape. So in principle, this slice of bread can be moving around this extra dimension in the shape of a circle.
Symmetry of U1 symmetry.
Now, here's the interesting thing. If I want to send a signal to my friend who's far away on our slice of bread, you would think the easiest and fastest way to do that is send a light signal along the slice of bread.
Right.
Just ignore the extra dimension. That's just superfluous, if you want to get there as fast as possible. We found, however, that if you are moving, if your brain is moving in this extra circular dimension, there's a faster way to get the signal to your friend. You don't send the signal right along the piece of bread. You send it in the circular dimension, allow it to wrap all the way around the circle, and then hit your friend.
Because it's moving. It's a Galilean relativity now. You're boosting it.
Well, but it's really special relativity and Lorentz symmetry that comes into the story here when you do the mathematical analysis. But yes,
in the combined rotating brain along that one special axis.
Yeah.
So would there be anisotropy? I mean, would you have this violation also in spatial?
Yeah, you do have you have a kind of left-right violation, because the question is, are you moving clockwise or counterclockwise around the circle? And that can affect the results that you get. In fact, it does affect the results.
Can you have weird time and causality issues?
Well, so causality is the big one. Because normally, whenever anyone says, I can send a signal faster than the speed of light, which is what we are saying, the response of most physicists will be, oh, that's interesting. You must be violating. That's right. You must be violating causality. Because if you can send a signal faster than the speed of light, we're trained to conclude that causality must be violated. That training is actually wrong. Because here's the thing. What you really need to determine is whether there are so-called closed timeline curves. That is, can you send a signal to your friend and have your friend send the signal back to you and have the return signal get to you before you send the original signal in the first place? Because let's say that return signal killed me. How would I be alive to send the original signal in the first place? So we did that calculation. We did the round trip travel time. I send a signal to my friend. The friend returns it to me. It will always get back to me a smidgen of a second after I've sent the original signal.
So
it can never get back to me.
Causality is built in. So yeah, I'm reminded a little bit of famous Gödel's. He also had a
Gödel universe.
Gödel universe. And then I believe he sort of went to his deathbed believing that was true, and he was a character for sure. And wow, that is really fast.
But let me just answer the other question you mentioned before. You asked me in terms of how fast can the signals go, and so our calculations show that when I send the signal to you far away on the brain, the speed of that signal can be arbitrarily large.
Wow.
And in fact, the formula for it uses a very famous symbol called gamma that we all teach to our special relativity students. Again, Lorentz. I usually don't talk in mathematics, but why not?
The smartest audience
so gamma is 1 over the square root of 1 minus v squared over c squared. Now, normally, that is a factor that we use in special relativity to talk about length contraction. You divide by gamma, or time dilation. In this particular case, it enters differently. It enters as the speed of the signal. The speed of the signal is not 1 over gamma. It's gamma, or gamma times c, if I put c back into the story. Gamma can be arbitrarily large, and therefore the speed of the signal can be arbitrarily large. Now, what does that mean? Normally, when we talk about the possibility of aliens, and I'm just using this,
we have to talk about this. Is podcasting in 2023.
Yeah. So this is no, so maybe I shouldn't even use this language.
No, keep it. You can't drop the A-bomb.
All right. So imagine there is some extraterrestrial civilization far away. Normally, we say Well, it'd be interesting to know they're there, but we can't really have a conversation because we'll say hello, and then like 100,000 years later, we'll get the signal, and then 100,000 years later, again, we'll get the return signal. We won't even remember that we sent
setting
it.
up this podcast with you. You're so busy.
Yeah,
but no, anyway.
exactly. So that would suggest that you can't have real-time communication when the other person at the other end of the line is too far away. In this approach, we can have a real-time conversation with a civilization arbitrarily far away, because we can get the signal there arbitrarily quickly if we are moving sufficiently quickly in this extra dimension. And then they can get it back to us. And it will always arrive after we sent the signal, but it could be a second later. So we'll say, hey, how you doing? Oh, we're doing fine. Oh, really? What's going on? And you could, in principle, right, in this universe. Now, I'm not saying that this is necessarily our universe. No. I don't know if there's an extra dimension. I don't know if there is one. It's in the shape of a circle. Mm-hmm. If it's there, I don't know that we're on a brain moving through it. But what's beautiful to me about this example is Einstein wrote his paper 18 years ago. Yeah. Okay. One would have thought that there's nothing else to extract from thinking about Einstein's special relativity. It's ensconced in the textbooks. We teach it to our students. It's done with, right? And yet, by just imagining this little generalization of Einstein, where you have this extra dimension in the shape of a circle, you extract these wonderful new results. So you asked me when we started, what does a theorist do? Yeah. Here's what a theorist does. Yeah. Now, usually we don't go back to Einstein in 1905. Right.
Although,
we stay.
I get a lot of emails that Einstein was wrong.
Exactly. But normally that's more in the crackpot domain. But here it is, going back to Einstein 1905 and doing rigorous calculations and coming to something which, to me at least, was shockingly unexpected.
And as I said, I think I would, if you gave me, or God gave me, the choice between, say, verifying that, inflation is consistent with, this production of gravitational waves from early universe tensor perturbation, or, which kind of a lot of people assume is true. I actually don't. I want to get into cosmological alternatives. But if you assumed you had that choice, or you could prove that Lorentz, invariance is violated, to me, that's the holy grail. And in fact, I want to get your reaction to this, because I can't resist. Again, we're in this building, this historic building on the campus of Columbia University. And Chien-Hsim Wu, when she discovered in the course of like Christmas break, she got down to 3/1000th of a Kelvin in an apparatus with a radioactive spinning cobalt nucleus that she magnetized. Just a triumph. I mean, we can't do that today. I mean, it's not like it's some easy thing that, you can go, like most of our experiments in our lab classes at San Diego, they're previously, won Nobel Prizes, Davis and Germer or Millikan oil drop or whatever. This, my students are not going to do. It's cost $1 million just to get a dilution for it they could possibly do. Anyway, she verified that the weak force is as maximally parity violating as possible, which you couldn't, think of as another kind of symmetry that could be respected under the grand rubric of all possible symmetries that nature could be expected to respect. We found that electromagnetism later is unified with the weak force in the work of Salam and Glashow and Weinberg that we discussed earlier. Is it possible that not only the strong nuclear force would exhibit parity violating properties, but also potentially electromagnetism? And I'm speaking now of things like Chern-Simons, cosmic birefringence, and things that we're looking for actively. And actually, Jim is hoping that we'll discover it, because Brian, we got him an asteroid. I got an asteroid named after Jim Simons. That was great. He's got a boat. He's got a plane. He's done it. But the one thing he doesn't have is a Nobel Prize. And so every year he talks to his friend Frank Yang, because you can nominate people who for the Nobel Prize if you've already won one, which unfortunately I have not, so I can't nominate him. And I wrote a book that's kind of condemning of it. But I want to ask you: is it possible that not only electricity and magnetism might violate parity at some level, but gravity, because all the forces are unified? If unification is true, or if you don't see it, does it mean that unification is impossible?
The bottom line is I have no idea, and I don't think anybody really does. Again, what do theorists do to that question? One of the things that we do is we take established theories and we add new terms to them in order to break some cherished symmetry or some cherished principle, and then try to determine through mathematical calculations whether this new term violate something else that we've already confirmed experimentally? Or does it give rise to a prediction for something that we can go and look for? So there are a gazillion papers which do this. And of course, the challenge to the experimentalists is, which ones do you take seriously enough to actually put the effort in to try to test? So, far be it for me to pass judgment on, a whole body of work where all sorts of symmetry violating terms have been added to various theories. It's exciting to imagine that something new and profound can happen even in the most well-tested theories, but I think it unlikely. But of course, the prize is huge if the unlikely thing actually bears fruit. So I don't know.
So I want to pivot from the very small to the very large and talk about cosmogenesis. I would say, why are people so interested in this? And all you have to do is I'll ask you, what's your favorite day on the calendar?
My favorite day on the calendar. I guess I'm supposed to say my birthday, but I won't. Is that what you were looking for?
It could be your birthday. It could be your anniversary. It could be when your kids are born.
I wish I could give you my anniversary. I just don't know it. It's either October 9th or October 10th.
Tracy,
blame him. Well, thankfully, both my wife and I both completely get it mixed up. So I'm going to go for October 9th.
Good.
Yeah.
And I think you're born on February 9th. So the 9th part is easy, right?
That's true, yeah.
So a couple days before Galileo's birthday on February 15th.
Yeah.
I always ask people that because usually it's the beginning of something. And people are always fascinated with beginnings. And I think the universe is no different. And I think that explains the surfeit of ideas for cosmogenesis, right? And among other things. But when you look at the kind of spectrum of models, we discussed candidate alternatives. I don't like to say that to string theory, but let's examine work that you've done and others that we both know have worked on that purport to explain things other than requiring inflation. I'm thinking of conformal cyclic cosmology with our mutual friend Sir Roger Penrose, Paul Steinhardt, Anna Aegis, Neil Turok, and their bouncing and cyclical cosmologies. And even my current office was occupied by Jeff Burbage of quasi steady state cosmological fame. And I actually talked to Giant Narlikar not too long ago on the podcast, the sole remaining survivor from the quasi steady state days. So when you look at these models, a lot of them start from the starting point that inflation and the multiverse that comes concomitantly with it. In most models of inflation, you have the multiverse. Andre Linde said that very thing on this podcast. They find that distasteful. Paul Steinhardt, good friend of mine, has said that not only is the multiverse dangerous to science, it's dangerous to society because it undermines the efficacy of the 400-year-old scientific method pioneered by our hero Galileo and many others. So I want to ask, is that a valid reason to kind of pursue alternatives? Is the multiverse so anathema to not only let's leave society out of it? I think society's got its own problems, but what's your take? Is the multiverse a problem? Is it an opportunity?
I have to say I'm a little bit surprised that Paul went that far in his critique of the multiverse, because there is something very real to say, and he's been saying it loudly and with intelligence for a while, which is the following. If you want to make predictions in the context of a theory that involves other universes, you've got to have some means of saying which universes are more likely and which universes are less likely. Because if all universes are out there, then all manner of physical phenomenon, all manner of observables, all manner of values of those observables takes place in some universe. And if you have no means of saying, well, yeah, those universes are incredibly unlikely, and this one and that one are very, very likely, and therefore I believe that those values are the ones that are most likely. If you can't make, that's right, if you can't make a statement like that, you are lost from the standpoint of making predictions. So Paul, this is called the measure problem. You want to be able to place a measure to say, this one's likely and this one's not likely. Now that's a scientific question, to try to come up with a means of assigning likelihood to given universes. It's not a problem that we've cracked, but there are many proposals, many mathematical ideas that people have put forward. And so I find it surprising that Paul would go further than that and say this is somehow fundamentally like bad for science, when there's a real scientific issue on the table. And if you can resolve that scientific issue, then this fits squarely within the scientific method. It's a little bit different in detail, but it's still, you have a idea, you develop it mathematically, and from that you make predictions. Because once you have a measure, you can make predictions. So that's a little bit surprising. But coming back to your question, Yeah, I would say the following. If we could resolve all puzzles in physics without recourse to a multiverse, my inclination, more like an Occam's razor approach, would be to take those ideas most seriously first. But if we continually run into a brick wall in trying to answer fundamental questions in a single universe framework, and we can answer those problems in a multiverse, a multi-universe framework, we should at least allow that to be part of our toolkit. We should allow it to be among the ideas that we take seriously and pursue it mathematically. And for instance, try to answer this measure problem. With that, we are doing science. And so I think that to me is the most rational and sensible way of thinking about it.
And what about the syllogism that, and I use this to, butter my bread in the Keating household, but, that if you measure gravitational waves in primordial form via their imprint on the cosmic microwave background's B-mode polarization, as we claimed to do about 8 years ago, and then recanted, and now have an opportunity to detect it again for the first time with Simons Observatory, Bicep Array, and many other experiments. If we do that, then that will be circumstantial, but the strongest possible evidence that we could hope to measure of the epoch about a trillionth of a trillionth of a trillionth of a second after the Big Bang. And therefore, that would be indirect evidence for the multiverse. In fact, on the day at which the Bicep 2 announcement took place, people like Max Tegmark, mutual friend Max Tegmark, would say things like, hello, gravitational waves, hello, in a multiverse.
Yeah.
And it was almost, almost too Hollywood perfect for his book, The Mathematical Universe, to resist. So I want to ask you, at what level does that syllogism curry favor with you or hold water with you? In other words, I tell you tomorrow, Brian, here's some secret information. Simons Observatory measured it. Would you believe the multiverse more ever?
No, so not quite that quickly. So generally speaking,
I'll say it's confirmed, by the way.
Yeah, I get it. But I would generally say the following. It's certainly the case that if you have a theory that predicts a multiverse and also makes a whole variety of other predictions that you really can test and confirm in our single universe, then of course that adds weight to the prediction of things that we can't confirm directly. So yes, I do agree that evidence of a theory can accumulate from observations in our universe, and that allows us to take seriously predictions for things that we can't yet see. However, it's also the case that there may be competing explanations for whatever it is that you're confirming in this universe, and those other explanations may not involve a multiverse. And indeed, I think that's where we're probably going in this conversation, because yes, were inflation truly the only game in town, the only cosmological theory that can give us insight into the cosmic microwave background radiation, solve the horizon problem, solve the flatness problem, give us all of these insights into things that we observe in our universe, and also, by the way, it predicts a multiverse, then sure, we'd be led in that direction. And yes, your example of finding that primordial gravitational waves would be one more piece of observational evidence in our universe, and that would be an interesting and tidy story. But there are other ideas that people have put forward, and those proponents claim that they can explain all the things that I just mentioned, the horizon problem, the flatness problem, and so on and so forth. And that would be interesting to see. Now, in this very specific case that you gave, finding primordial gravitational waves, these competing theories, and one in particular, Paul Steinhardt, doesn't give rise to that.
Rogers' theory doesn't give
it doesn't rise to it. But these are simply the ideas that we've developed to date. And so I would not immediately jump to the existence of a multiverse if you were to come to me with that data, because I would say, let's allow our brains to continue to strive and see whether there's a single universe theory that does comport with everything. Again, I wouldn't rule out a multiverse. I've written a whole book on the multiverse, right? So I'm not anti-multiverse.
No, I know.
But I am reluctant to jump so quickly to such a radical proposal of other universes. I would rather say, hey, this lends credence. It increases my Bayesian probability that this idea may be true. However, I'm going to still hope myself and others, inspire others to continue looking for more pedestrian explanations that don't involve a multiverse. And if 10 or 15 years later, there's nothing comes up, yeah, sure. Then it becomes even more
the
compelling.
lone survivor.
You know.
Just before we pivot to our maybe final couple of topics, if you do you
Sure,
have
yeah,
any more minutes?
yeah,
Okay,
totally,
good.
yeah.
I've definitely got my second and third win being here with you, Brian. It's so exhilarating. So you view the multiverse as a prediction. Actually, I've never heard it phrased like that. In other words, I've heard it phrased as a consequence, a paradigm, but not a prediction. And I think that's an interesting way to look at it, because I would say that inflation is very successful when it comes to retrodictions, in that it explained, Dickey's conjecture of the paradox, the fine tuning of the curvature of the universe. That even in the 70s they knew it was around 1, it wasn't 0, it wasn't infinity. And then the oldness or the horizon problem, those are kind of retrodictions that you want your theory to explain. But the novel prediction, and even I do believe that B modes or primordial tensor perturbations in and of themselves per se are are novel effects that would falsify, not prove inflation, but falsify alternative rivals.
Yes.
Right? So in that sense, what would you like to see in a candidate? You talk to God, right? And so you say to God, I want a candidate theory that replaces. I'll tell you what I would like. I would like for these alternatives to not have the kind of sine qua non of inflation, which is the inflaton field. I would like to have a theory, and none of them have it today, have a scalar field free version of a cosmogenic event. And maybe I'm wrong because I'm not searching this. Sir Roger has he doesn't have a scalar field in the sense that Anna Aegis and Paul Steinhardt do, but he has these errabons, these mysterious dark matter particles that act like the creation field of Hoyle. Do
you know it at a level of detail? I don't. Yeah, I don't know about that.
What I would, if I was, a good theorist or a theorist at all, I would say I want to invent a theory that's at least like inflation as possible, which means not having a sine qua non, which means I'd like it to not have a scalar field. What is your minimal universe? What would be the minimum viable product that you would ship as a theorist, to say that here's an alternative to cosmogenesis that doesn't look like inflation, it doesn't have these features in it? What would be your minimum viable?
Well, I'm not sure I would go in the direction that you go.
Okay.
I find inflation actually a beautiful mathematical theory.
Oh, sure.
Including a scalar field, the most simple kind of field that there is, and one that we now know does exist. At least the Higgs field is a specific example of a scalar field. So it's no longer this hypothetical thing that it was when it was first introduced into inflation. Right. Now we know there are fields that have this quality called being spin zero and being a scalar field. It's a very beautiful theory. It makes use of this spectacular feature of Einstein's theory that gravity can be repulsive as opposed to just attractive. That's a beautiful quality of the theory. And it so elegantly resolves many cosmological problems that people scratched their heads over before the theory was put forward. So I don't look at inflation and say, let's God do one better than that. But what I would say is inflation doesn't resolve all questions. For instance, where did these fields come from? Mm-hmm. Why is there a universe at all? Right. What happens at time zero? Because even though inflation changes the nature of time zero, it doesn't allow us to truly answer the question of how things got started in the first place. Mm-hmm. It's still a theory of how things evolved from a tiny fraction of a second after whatever created the environment and the ingredients that allows the theory to clock forward. Mm-hmm. So those are the questions that I would want, the all-powerful being to resolve, or give a theory that transcends inflation and can embrace answers to those questions.
So in a sense, the inflation may be that minimum, Occam's cosmology, in a sense.
Yeah.
I want you to get your reaction. When physicists get older, they devolve into the interpretations of quantum mechanics. But I want to get into the interpretations of the multiverse, having written books on this yourself. It's never been clear to me why, in both the multiverse and the string landscape, why we say things like there'll be different vacuum states, and those could lead to not only different constants of nature, but they could lead to different laws of physics. I've heard that said, and you're shaking your head, so maybe I'm correct. I've certainly heard people say such things. I don't know if it's actually true. But my question to you is perhaps a philosophical one. Why stop there? Why not say, actually, there are different laws of mathematics, and even
different laws of so-called predicate logic. In other words,
Sure.
in different universes, modus tollens doesn't work. And not only is the different is G, capital G, 9.9 meters per second square, or whatever, the gravitational force, lowercase g, but it's actually it doesn't follow that if A then B and B doesn't follow,
Sure.
right?
So
Could it be that we have a different laws of philosophy, mathematics, and logic?
So it's an important question to ask, because the answer requires that I spend just 1 minute, a little bit more detail on where the multiverse comes from. Say in a theory, let's use string theory as an example, or in string theory coupled with inflation, if you want to talk about the process by which other universes might come to be. So the idea is that there's one overarching mathematical structure that applies to all of these universes. And it's simply, in string theory, say that the extra dimensions are curled up in different ways in these different universes. But because the overarching mathematical structure is still string theory, it's just string theory in a universe with the dimensions curled up like this, or string theory in a universe with dimensions curled up like that. So in that sense, the equations are the same, and it's just environmental differences, the shape of the extra dimensions, and that's really all that it is. So that's why I would say it's not even that the laws of physics vary from universe to universe. It's that the laws of physics manifest in different ways because the environment changes from place to place. I mean, we're all familiar, gravity on the moon seems different than gravity on Earth, right? Astronauts can jump 20 feet into the air. But we all know that it's still the very same law of gravity, the
universal.
That Newton wrote down, or Einstein, whichever take your pick, the level of accuracy. It's just that the environment is different. Because the moon is less massive than the Earth, gravity manifests somewhat differently on the moon than on Earth. And that's the way in which these different universes differ. Same overarching mathematical structure, same overarching formulae, but the way they manifest can change based on the shape of the extra dimensions. So that's why it's not going to different logics and different kinds of mathematics. It's really a uniform quality that permeates all of these universes. Now, having said that, you can use your imagination to imagine more robust versions of a multiverse where, you could imagine that the kinds of mathematics that take place is different, continuum mathematics, periodic mathematics, or the different kinds of logics can differ. Those multiverses, though, are coming directly out of the human imagination. They're not coming out of a rigorous mathematical theory like string theory or inflationary cosmology. It doesn't mean that those ideas are wrong, but they're just less motivated because they're just coming from a what if standpoint, as opposed to here's this theory, we study it, and oh my goodness, look what comes out. A multiverse, because there are different ways for the extra dimension to be curled up, or there are different big bangs in, say, an inflationary multiverse, giving rise to different swelling domains, each of which should rightly be called a universe of its own. Those multiverses come directly out of the mathematics, and that limits the ways in which those universes can differ from each other.
I see. Okay, excellent. So you are going to pivot now to two last topics. One is education and pedagogy. And the last one is aliens. By law, we must talk about aliens, and then it's either aliens or Bitcoin. Which would you prefer, Brian? Up to you.
Yeah, we'll go. They're kind of the same. But
No. All right, send your hate mail to this Brian, not to this Brian. Education.
Yeah.
You're a renowned educator. I've learned a tremendous amount from you. I saw you first, met you in person back in 1995 at Brown University, where I was a grad student. You were, I believe, moving from Cornell to this very location, and your career, and it was, what is it, about the anniversary, or your book had just come out maybe a couple of years earlier. And you've taught millions, and you continue with your World Science Festival, that you have this phenomenal team, and you and your wife are doing so much effort. First off, how do you envision the role of a scientist as an educator? And I'll make a bold statement. I believe it's my moral duty to have a podcast, to give a lecture, to make a TikTok, to do something based on the fact, A, I'm teaching at a public university, but all of us were supported by the public. We're all serving at the largesse of the American taxpayer, or whatever government you're in or work for, or live in rather. And I believe that we take a lot, and we would do this for free. I mean, you and I have such pleasure in finding what we do as a living. I think we do it for free, more or less. At least I would. I love building and tinkering and playing around with physics. But a lot of my colleagues will react negatively to that. They'll say, no, stay in your lane, stay in the lab. It's too hard and we're not good at it. Obviously, I haven't had like much training in terms of like podcast, as you can probably tell. I'm always learning, but I know that people have investigated it. And I also say to people, I had a battle with Sabine Hassenfelder, who's my curmudgeonly friend from Germany, who has a wildly successful podcast. And she said, yeah, stay in your lane, basically. And I said, well, why? And she said, well, it's really hard. It's very difficult. It's not in the skill set of most scientists. So why force them to come out of the laboratory to go into the, and I said, Sabina, to be fair, like, did you come out of the womb knowing quantum field theory? No, it was hard and you learned it. And to say that something is hard, so we shouldn't expect our students and actually to teach them that communication with the public who feeds them, who pays their, is unimportant, or that they should ignore it. I think we do that at great peril, not only to the public understanding of science, but to science itself. Because once the public loses faith in science and scientists, that we're just these specialized insects working on one thing, and that's too hard for them to understand, they're going to stop funding. I would stop funding. As people said, you're not smart enough to understand what I do. You can't even explain it to somebody. So I said a lot, but let me know, what is your feeling on the minimal obligation of a scientist to explain his or her work to the general public?
To go out to the public and to explain what you're doing, you kind of got to enjoy it, right? So I get the feeling that you do enjoy doing this,
I'm a
right?
narcissist, so I love doing it.
Yeah,
Self-promotion.
And so anybody, they're not all physicists would like to be doing this kind of work. And so to imagine that there's some moral responsibility or that everybody should do it, that seems to me not necessarily a productive way forward.
I hated linear algebra. I mean, I just detested it. It was so boring. It's just rote memorization. I wasn't good at it. Should I not do it? I mean, because it's uncomfortable and not easy for me?
Well, I would say that you probably did it because you wanted to learn quantum mechanics, is my guess, right?
I actually was like a civil engineering major for a week,
but you had motivation to learn it because but for some physicists who are right at the edge. I mean, take someone like Edward Witten, right? Who's actually a wonderful popularizer. So this may not be the best example, but if you were to say, Edward, you're not doing enough for the public. Yeah, you do some interviews, you did a wonderful World Science Festival program, but you've got to have your own podcast, Edward. Morally speaking, you've got to be out there. I don't think it would be the right thing to force him, because I'd rather have Edward.
But he is doing it because he did the World Science.
That's right. So the point is, I think every physicist, if we stick to our field, needs to determine for themselves how much they want to do and how much they're interested in doing. And if there's some who don't want to do it at all, I'm totally fine with that, because I don't feel like you should force someone to do something of this sort.
Let's not take the Witten example, because I mean, it's just the primus inter pares, or whatever the Latin phrase is. Let's take your grad student.
Sure.
Should she not do it? Isn't it not good for her to develop confidence talking to the public, talking to a camera, talking and purveying? A lot of what you and I do is persuasion, it's salesmanship, and we have to be good at convincing funding agencies, tenure committees, admissions.
But those are all somewhat different skill sets.
Sure, I know.
So it's certainly the case that students need to learn how to write a grant, and in a grant, you need to be able to describe your work in a way that's exciting and accessible. And if you don't do that, it can have really negative implications. Yes, certainly on that front. And when I look at my own graduate students, there are some who absolutely should go out into the world, and some of them have in terms of explaining it. There are other of my graduate students that I really do not think it would have been the best thing for them to go out into the world, and many of them haven't. But having said that, one of the things you mentioned, the World Science Festival, we try to provide a platform where scientists from around the world can come and maybe not do a podcast where it's going to be every week, but maybe come once a year and talk to the public in a way that can really have impact. So yes, I partly agree with you. I think it's obviously vital and important, but I wouldn't necessarily say that it's a moral responsibility of everyone to do it. Rather, if you're driven to do it and you enjoy doing it and it's fun doing it and it's productive doing it, by all means
Yeah.
do it.
I think you should try it and see if it does appeal. You know, water the fertilized ground
For
and
sure.
see what comes up.
Yeah.
So, but sticking with education, you and I are part of an august profession, you know, being professor. I always say, what's the proof, Brian, that being a professor is the greatest profession on earth? I don't know if you have a proof, I have a proof. What was the only career suitable for the most famous man on earth right after he walked on the moon's surface? Neil Armstrong became a professor at the University of Cincinnati.
Oh, is that true?
He was an engineering professor, and that's he lived out the rest of his life. Now, the guy could have done anything,
right?
And he was very satisfied in doing that. And to think that, you know, we get paid to do it, I would say it's like being, you know, paid to taste chocolate or be a wizard and, you know, Harry Potter. But we get to do this great thing, and yet our profession's pretty damn sclerotic. I bet, you know, when you were at Oxford, when I was at Brown, you know, there was some person scratching on, there's a beautiful bespoke chalkboard, floor to ceiling with your Harry Gumo chalk probably over there. No, it's like Crayola. How could you, Brian? You're letting down generations of theoreticians. But there was some guy or gal scraping on a rock with another piece of rock, as David Kaiser always talks about it. And this goes back to the year 1080 in the University of Bologna, where the first Western university was established. And look, okay, so I use PowerPoint or Keynote rather. Okay, not much has changed. What do you see as threats or opportunities for pedagogy in the 21st century with maybe new tools like artificial? Why should my students learn from Brian Keating when they can learn from Brian Greene virtually with an avatar in 3D, you know, at the speed of light?
I think you're right. Not that your students should learn from me, but that there are huge opportunities. So one of the things that we've been developing are virtual reality experiences. We have a virtual reality experience for middle school kids where they can build stars and have them go supernova. We have another experience where they play a game where as they progress in the game, they go faster and faster, getting closer to the speed of light, and all the weirdness of relativity comes out in the virtual reality experience. So they can get a more intuitive sense of these ideas. So I think there's a huge opportunity using that kind of medium for science to become much more internalized as opposed to just seeing it written on a blackboard. In terms of education itself, I agree too. You know, a handful of years ago, I did a course you probably haven't seen on special relativity, where, you know, I basically, again, it was a purely digital course, but I was using at that time cutting edge technology, which is basically 8-foot wide iPads in which I didn't just use the chalk on a chalkboard, but I could write, I could show video, I could do demonstrations. And so to me, that was a personal proof of concept that you could use these tools to create. Look at that. I just knocked your microphone over. Sorry about that. Are we still working? Yeah. You know, that you could use these tools to really radically change the educational experience. Right now, we're doing a new course in quantum mechanics, which will be for the general person, but it's the full college level quantum mechanics course, chock full of visuals, chock full of interactive demonstrations. So I agree with you. There is a way to go beyond what we've been doing for, I usually say 500 years, but if you go back to 1080,
gotta go.
You're taking, you know, almost 1,000 years. You know, so yeah, I absolutely agree.
I'm really excited about it. At UCSD, one of my colleagues is working on AI avatars that use voice synthesis, use clothing from video game, Unreal Engine to synthesize Gandhi. Or I've taken all of Feynman's works because they're all public domain now, and I've digitized them. And we have a Feynman bot on my website that you can communicate with as if he's sitting right there. Now, but you can imagine the visceral nature, because people in Maslow's hierarchy of needs, and you look at how do people learn and what's the primacy of learning and the exposure, and the more visceral you make it, the better. And I think, you know, you as an educator, you know, are really kind of doing yeoman's work along with your team and your crew. How do you decide, you know, how to allocate your time? We talked about what you do, but you're doing so much with WSF, and you're making time to do, you know, podcasts with nobodies like me. But Brian, how do you determine, like, I'm going to do an explainer video, I'm going to do this fabulous TED Talk seeing my 6 million people, I'm going to do WSF every single year for the past 15 years. Yeah. Unbelievable. So how do you decide, just what's your day, what's your workflow like?
Well, it was the case years ago when I was a assistant professor at Cornell, which is really when I started to do stuff more generally for the public. My strategy was pretty straightforward, which was I would do physics by day, And then sort of by 6 p.m., I'd go home, eat dinner, and then I'd do the other stuff by night, writing articles, writing books. The Elegant Universe was written totally in the evenings. I diligently did not allow these two different types of undertakings to interfere with each other. But then what happens is you get older, you get married, you've got kids. And now all of a sudden evenings didn't exist any longer.
I had to go write a kid's book.
Yeah, well, that's true too. But that's when things really changed for me, really when I had my first child, which I guess that was 2005. And then it really came down to a decision. Do I spend my time on X or on Y? And in the early days, I struggled a lot with that, really trying to find the balance. Okay, I did this many hours of research this week. I gotta do more next week. Or, it was that kind of thing. And finally, I got to a place and I said, look, life is short. And this struggle that I'm creating for myself is totally in my own head. I can do whatever I want. And I just decided, let me just do whatever feels right at a given moment. And so if it felt right to jump into a book, and that meant that research projects had to go on hiatus or even on complete hold, so be it. Then some interesting research project would crop up at some point later and say, drop the book and work on the research project, because that's the most exciting thing at a given moment. So I stopped evaluating it. I stopped judging myself. And I said, let me just live as an individual who likes to do research and to write books. And, I've written stage pieces. We had things of that sort, World Science Festival programs. I like these kinds of conversations, and let me just go with the flow and see where it leads. Wow. And that's been a perfectly fine and happy way of going forward,
So we're coming up this Thursday, I believe, is the 90th birthday of Carl Sagan, speaking of Cornell. And Carl, of course, is known for many things, but one of my favorite things that he did, I guess you did it with Icarus at the edge of time, it was write a fiction book. And the fiction book is called Contact, loosely based on our past guest, and also Cornell alumna, and maiden name Cornell, which is Jill Tarter. And of course, these are subjects revolving around our final topic, which is aliens. So much is in the zeitgeist of aliens, the spirit of the time, the news cycles. We've had NASA panel led by the president of the Simons Foundation, David Spergel, eminent National Academy of Science member, leading a NASA panel to talk about these unidentified aerial phenomena. What do you make of this? What do you make of the eyewitnesses? I've had on a couple on my podcast, Navy fighter pilots, doing stuff I could never have the bravery or physical fitness to do, obviously. What do you make about these? The eyewitness reports, the kind of technical, identification or examination. How do you look at it as a scientist? How should a scientist look at it?
Look, obviously, the right person to answer that question is, say, a David Spergel, someone who's really looked at the data and been on a committee to try to evaluate whether or not there's anything to this stuff. But if you ask me on the outside, my sort of gut feeling is it's all nonsense. Why do I say that? Well, for following simple reason, if an alien civilization had the capacity to travel across the galaxy, interstellar distances, do you really think that they'd be sort of hanging out so that a fighter pilot could spot them and like, oh my God, and they try to get out of the way really quickly and they just get caught on camera? I mean, it just seems so incredibly ludicrous to me. And then when you think of it in the context of timescales, right? Life on planet Earth evolved pretty quickly, 500 million years after the Earth formed. Couple billion years later, we start to get multicellular organisms. Intelligence then follows relatively quickly upon that. So let's say billions of years is the timescale for intelligence. Now, that would suggest that if there are other intelligent beings out there, and they'd have to be pretty intelligent to be floating around in our atmosphere, they are likely at a timescale that differs from us by the order of 1 billion years. Right? It's not as though the clock said go and evolution started on planet Earth and planet X simultaneously. Like a thing is planet X, if they're able to do interstellar travel, they're not just 100 years ahead, they're likely 1 billion years ahead. And 1 billion years ahead, just think about it. We'd be so uninteresting to them, right? How often do you stop and get down on all fours and speak to ants in an anthill? You
I
probably
don't want to say.
you don't
I don't
do
want to
it.
say.
That's
It's one of
right.
my hobbies.
You don't do it often because it's not interesting. And if other civilizations a billion years ahead
E.O.
of us,
Wilson would disagree with you.
well, that's right. That's right. So there are a few,
Right.
but the point is there's probably a billion-year difference in our evolutionary development. And so the idea that they'd be just in a ship that kind of looks like our ships, or in a flying saucer that kind of looks like the flying saucers that we imagine, no, they'd be a billion years ahead. They would be traveling in ways that we can't even fathom. And so the idea that we're just kind of catching them is so ludicrous to me. And more pedestrian explanations that I've heard bandied about, weather satellites, interesting phenomena where light bounces off, those explanations seem to be much more likely to me. And when you put it in the context of everything that I just said, it just kind of feels ludicrous.
Yeah. I mean, often you hear that these objects defy the laws of physics. And, one of the things I always point out was that, if there were a military, campaign to mock or sow discord or do whatever, they would make things that would appear to violate the laws of physics. My favorite, analog here is Louis Alvarez in World War II had these radar jamming and spoofing mechanisms that as an Allied plane would get closer to the German forces, it would actually broadcast weaker and weaker radar signals to it, declining as the inverse fourth power as a reflected signal would. So they thought, this thing's getting farther and farther when it's really getting closer and closer.
Wow.
Therefore, to the radar operator in Berlin, these things defy the laws of physics, but they had a perfectly. Now, I want to distinguish between extraterrestrial intelligent and crafts and life elsewhere in the universe. So I think where do you come down in that spectrum? Are we alone first and foremost, and then the secondary question of can we actually learn from, or I always say no one would like the aliens to be visiting us more than a physicist, because we'd be learning so much about them if they don't eat us or study, poke us with the magnifying glass like I used to do with my aunts. But I'm not going to talk about those crimes against ontology. So tell me, life in the universe.
Yeah, I mean, obviously we don't know, and there's this famous thing called the Drake equation, which I always recoil when people call it an equation. It's just an encapsulation of ignorance in a variety of terms.
Bars, right?
Yeah, it's So look, as we now have discovered 5,000 plus exoplanets, we're pretty convinced that planets circling stars is the norm. It's not the exception. So there could be hundreds of billions, if not trillions of planets in our own galaxy, and our galaxy is one of hundreds of billions. So there's so many opportunities for life of the sort that we're familiar with to take hold on a planet someplace out there. So when you take that into account and note that we now have evidence for, amino acids and, these things, these molecules necessary for life seem to be relatively ubiquitous. They're not that hard to synthesize and to be on any of these other planets. We'll know for sure pretty soon with the James Webb Space Telescope studying the atmospheres of a variety of exoplanets. How could you not say, yes, I think it's reasonably likely that there's other life out there?
I take a slight contrarian viewpoint on all these things, not just in the extraterrestrial. As a guard against confirmation bias and of the sort that I would love for there to be extra, to ask questions to see if you're right about string theory.
Now, that wasn't intelligence, I'm saying.
No, I know
just
that.
Life. Yeah,
but I'm also a contrarian and a pessimist and a minimalist when it comes to even life. Because I say, what if I told you, Brian, one of those exoplanets, I just heard, from one of my friends, and you can't check your phone to see if I'm true or not, if I'm telling the truth or not. But she told me that actually there's a planet. And there's a binary planet system. It's near a G-type yellow subdwarf, just like our sun. And one of those, they're both in the habitable zone. These two planets, different orbits, slightly different orbits. They don't interact gravitationally. But one of them is teeming with life. It has life in every extremophilic location you could possibly imagine. And we don't know yet because the James Webb has, got to tilt over and look at it or what have you, and actually see if there's city lights on this one planet. And I said, what do you think? As a good Bayesian, I hope you are, otherwise we can't be friends. No, but as a Bayesian, what would you say the probability is for the twin planet, the other planet? Maybe it's in the same orbit, maybe it's slightly outside the orbit, in the habitable zone, same composition. So what would you say is a guess at the probability that there's also at least single-celled organisms on that planet?
It seems reasonable.
It's pretty high, right?
Yeah.
So I would say, well, we have that example. It's called Mars, right? So Mars is in the habitable zone.
But it's also a dynamical question, right? So in fact, it could be that life on planet Earth originated on
That's
Mars.
absolutely.
I mean, that, you know, so
That's where I'm going. Yeah.
Yeah. Okay.
So the non-observation of life right now, at least to our understanding, there could be lava tubes, and Avi Loeb, our friend up at Harvard, thinks that he might find the alien skeletons, scraped on the side of the cave, which I want you all to do out there. The 4 words that are most important to humanity. Please like and subscribe. But the fact that we haven't observed it, not a lack of evidence, as your friend of mine, Carl Sagan, used to say, is not evidence of lack. But at the same token, we should be able to set some Bayesian, prior reduction based on the non-observation of life anywhere in the. Now, maybe we'll find it tomorrow. So I'm just saying there seems to be this prediction, as Carl and Ann Druyan, who was also on my podcast a long time ago. Carl wasn't, but Ann was, and their daughter Sasha was on, and it was wonderful. But as they said in Contact, they said, well, if there's no life out there, it's an awful waste of space. Now, I've been to Antarctica twice. I spent over a month of my life.
I've been there once.
You have? You've been to the South Pole. Right?
No,
I
can
trump you. Okay, fine. I got one thing over you, Brian. Come on. You're my avatar. But not much life there. There's more penguins than people. And even there aren't that many penguins in Antarctica. There's no life at the South Pole besides the people that are there. So just by saying there's possibility of life, like these exoplanets.
No, I totally agree.
Nothing about the actual problem. Okay.
Yeah. No, I completely agree with that. And so that's why I say it a little bit facetiously that, look, the ingredients seem to be out there, and there seems to be a lot of opportunity for the ingredients to take hold. But in detail, even giving a different example, what if we find that life on Earth only took hold because of this incredibly obscure phenomenon that we've yet to identify? And that phenomenon is so incredibly rare that it perhaps never happens anywhere, even if you got 100 trillion, that this is something that's at least possible.
10 to the 25th.
That's right. That's right. So if it's 10 to the minus 100 likelihood for this obscure process. Now, we've not found evidence for any such obscure but until we synthesize life in the laboratory and we actually know, hey, all you need are these very basic, a little bit of, electric current, a little
Calabi-Yau manifold.
That'd be a little bit too far. But, if you can synthesize it in the laboratory and it's really damn easy to do, then the likelihood of finding it elsewhere, I would err much more on the side of saying, yeah, I'm now much more in the camp of this is likely to happen. But until we do that, no, it could be that we're missing something deep.
Well, Brian, I want to thank you so much. I always conclude with your indulgence of a few more minutes with the following 4 questions that are existential in origin. But to get those,
just as long as it's not, why is this night different from all other nights?
That's coming up. That's coming up in the spring. We will touch upon something related to that. But if you want to hear Brian's answers to these, you have to subscribe to my mailing list. I'll have links to subscribe to the World Science Festival and all of Brian's cool stuff. And that is at briankeating.com/list. And if you have a .edu email address, because I love students and I want to encourage students to develop their communication skills and learn from these conversations, you're guaranteed to win a meteorite, a chunk of 4 billion-year-old space schmutz from the pre-Earth environment of our solar system. So that's at briankeating.com/edu. So go over there if you want to hear that and the answers to Brian's final 4 questions. But before we go, I just want to give you a business tip, a business proposal.
Sure.
And that's, you ever see these things? You can buy a star, Brian. You can get a star.
Star named. Yeah.
Yeah.
I think I may have even done it once.
That's what I was hoping you'd say, because I have an idea for you, and this is free of charge, and you feel free to use it. Why buy just a star when you can buy a universe within the multiverse? That is the World Universe Registry in the multiverse. Brian Greene, thank you so much for being on the Into the Impossible podcast.
My pleasure. Thank you.